Welcome back to the Explainer. Today, we are literally unlocking the hidden language of the universe. Have you ever wondered how physicists can predict exactly where a thrown ball is going to land, or exactly how long it takes a car to brake? Well, it all comes down to kinematics, the study of motion. We're going to build a layered blueprint of motion today, starting from the most intuitive, everyday observations and stacking those ideas until we hit the elegant mathematical equations that govern how everything around us moves. Let's get right into it.
Here's the layered blueprint we'll be following. First, the relativity of motion. Then, scalars versus vectors, followed by distance and displacement. Next up is speed, velocity, and acceleration, and we'll wrap it all up by actually deriving the equations of motion.
Section 1, the relativity of motion.
Okay, so an object is formally in motion when its position changes with time relative to a reference point, or an origin. The absolutely crucial thing here is that motion doesn't just happen in a vacuum. You literally cannot describe it without picking a fixed point to compare it to. Without that reference point, the whole concept kind of falls apart.
So let me ask you, are you moving right now? Take a second to think about it. You might be sitting on your couch, feeling completely at rest. Your position isn't changing relative to your chair, but are you truly still?
Well, motion is relative. Let's look at an airplane for a second. If you're on a flight cruising at 500 miles per hour, your velocity relative to the plane itself is exactly zero. You and the seat are just chilling together. But to someone standing on the ground looking up at the sky, you are absolutely hurtling through the air. You are simultaneously at rest and in motion. It just depends entirely on who's looking. That's the relativity of motion in a nutshell. All right, section 2. Scalars versus vectors. To measure all of this, we divide the physical world into two distinct camps. On the left, we've got scalar quantities. These only have a magnitude, which is really just a fancy word for a numerical value. Think of mass or temperature. 5 kilograms of apples is just 5 kilograms. Direction doesn't matter. But on the right, vector quantities. Vectors need both a magnitude and a specific direction to actually make sense. Driving 50 miles per hour is a scalar. Driving 50 miles per hour north? Boom, that's a vector. Moving right along to section 3, distance and displacement. Now here's where it gets really interesting. Look at the fundamental difference between distance and displacement, two words we mix up all the time. Distance, over on the left, is the actual, literal path you traveled. If you take a winding, zigzag path through the woods, every single step adds up. It's a scalar quantity, and it's always positive. Displacement, on the right, completely ignores your winding path. It is strictly the shortest, straight-line distance from your start to your finish in a specific direction. That makes it a vector. Which brings up a super fascinating question. Can you move a certain distance, but have absolutely zero displacement? The answer is a massive yes. Imagine running a full 400-meter lap on a track. You sweat, you work hard, and you cross the finish line right where you started. Your distance traveled is 400 meters, sure, but because your starting and ending positions are exactly the same, that shortest straight line is zero. Your displacement is literally zero. Next up, section 4, speed, velocity, and acceleration. Just like distance and displacement, speed and velocity are totally different beasts. Speed is simply distance covered divided by time. It's a scalar. It just tells us how fast you're going. Velocity, though, is displacement divided by time, making it a vector. Basically, velocity is just speed moving in a definite direction. And here's the kicker. Because displacement can be zero, like our track runner, average velocity can also be zero, even if your average speed was off the charts. But what happens if you speed up, slow down, or turn? That is acceleration. Acceleration is defined as the rate of change of velocity with time. It's a vector quantity measured in meters per second squared. Hit the gas in a car, you get positive acceleration. Hit the brakes, your velocity drops. In physics, we actually call that negative acceleration, or retardation. And there is one acceleration number you feel every single day, 9.8. When an object is in free fall, moving only under Earth's gravity, it accelerates downward at a constant rate of 9.8 meters per second squared. So every single second an apple falls from a tree, its downward velocity shoots up by 9.8 meters per second. Finally, section 5, deriving equations of motion. Let's put all this together and look at the velocity-time relation. Don't let the letters scare you, it's really just logic. We start with our basic definition of acceleration. A equals final velocity, v, minus initial velocity, u, all divided by time, t.
Multiply both sides by t, and you get at equals v minus u. Rearrange that by moving u over, and boom, our first fundamental equation, v equals u plus at. It tells us exactly how fast something will go after a certain amount of time, assuming constant acceleration. Let's see how this builds into the displacement-time relation. We know average velocity is just initial velocity plus final velocity divided by 2. And displacement, which we represent with the letter s, is average velocity times time. If we take that first equation, v equals u plus at, and just substitute it in for v, the math beautifully simplifies down to s equals ut plus 1/2 at squared. This clever little equation calculates exactly how far an object travels while it's accelerating.
And that brings us to the displacement-velocity relation. What if you don't know the time? No problem. We take our first equation, rearrange it to solve for time t, and plug that expression into our basic displacement formula. Simplify the math, and you get v squared equals u squared plus 2as. It's an incredibly powerful tool because it links speed, acceleration, and distance, and you don't even need a stopwatch.
Before we wrap up, let's look at one final mind-bending concept: uniform circular motion. Picture a cyclist on a perfectly circular track, moving at a steady 15 miles per hour. Because they cover equal distance in equal time intervals, their speed is totally constant. But remember vectors? Velocity needs direction. Because the cyclist is constantly turning to stay on the track, their direction is always changing. That means their velocity is changing. And if velocity is changing, that cyclist is actually in a constant state of acceleration, even at a steady speed. Pretty crazy, right? And there's our blueprint. We went from staring out an airplane window all the way to deriving the algebraic equations of motion. I absolutely love this quote from our source material. Life's velocity will always change. Just make sure you are in the right direction. Physics isn't just crunching numbers. It's a framework for understanding reality. Direction changes everything, in math and for sure in life. Thanks for tuning into this explainer. If our velocity as humans is constantly changing with every choice we make, what direction is your acceleration pointing today?